we'll try to understand a little more about conductors in electrostatic conditions. You may say, well, didn't we already do this at the end of chapter 24? Sure. We understood that you take any arbitrary shaped conductor, the electric field is 0 inside the body of the conductor, right? And at the surface, the electric field is always perpendicular to the surface. We also saw that if you put any excess charge on a conductor, it will all go to the surface of the conductor. And at the surface of the conductor, electric field has a magnitude that's sigma by epsilon 0, where sigma is the charge density, the local charge density in the neighborhood of that point. You see? So these were all some wonderful properties of conductors, and we looked at various applications. The one last question that we want to answer here is, how exactly does the charge distribute itself on the surface? Does it depend on the shape of the surface, right? So that's the question we try to answer here. And with our understanding of electric potential, we get a new insight into how exactly the charges distribute themselves on a conductor. Okay, but before I get to answer that question, just a little bit, we'll explore a little bit further about conductors. So since we have the expression delta V is equal to negative integral E dot dl going from one place to another, we see that if, say, for example, I put some charge on the conductor, and you've got a charge that distributes in a certain way, and then I've got a point charge, a test charge that I'm bringing from infinity. As I bring it, as I get closer and closer to the conductor, I'm doing more and more work because I feel the strength of the electric field. I keep doing more and more work until I get to the surface of the conductor, right? And so the most work would be right when I get to the surface of the conductor. But once I get to the surface, if I imagine going inside the conductor, I do not have to fight against the electric field anymore because there is no electric field. So to go from the surface to this point or to another point or to another point, I do the exact same amount of work, right? And since work done per unit charge is the potential, right, or change in potential, so what we are saying is the electric potential doesn't really change inside the body of the conductor, you see. So every point in the conductor is at the same potential as the surface of the conductor, okay? Or in other words, we say that a conductor is an equipotential. You see, a conductor is an equipotential. If you want to call it an equipotential volume, you can say that the whole body of the conductor is at one given potential, and that's why you hear the term the conductor is raised to a certain potential, right? You put some charge on a conductor, the potential is now maybe 100 volts with respect to a point out at infinity, okay? So that's what I've written here. V is constant everywhere inside the body of the conductor, and that's all equal to the value at the surface, okay? So given that, we'll try to apply that to a spherical conductor. So this is not a circle, this is actually a sphere, right? So this is a spherical conductor. Let's say the radius is r, right? Radius is r, and I put a charge q on the conductor. So it's a solid conductor, and everything is going to distribute itself. And since it's a beautiful sphere, the charge will be uniformly distributed on the surface of the conductor, right? So the sigma would be a constant. It's all nicely uniformly distributed. And we already have this expression for the electric field outside the conductor. So E is KE, divided by R squared. If my point is outside, the electric field is radially outwards, and R is the distance from the center to the point P, right? That's my R. So this is for R greater than or equal to capital R. And we know E is equal to 0 everywhere inside the body of the conductor, right? So this is a spherical conductor, right? Spherical conductor. So, so we have this for the electric field, and just like, and if you remember in the previous lesson or the 2 lessons before, we saw that these were exactly the same equations that we had for a spherical shell of charge, and we went through all these calculations, and then we showed that electric potential V for points outside is just KEQ divided by R. This is for R greater than or equal to R, right? So it behaves, for points outside, it behaves as if all of this Q is centered, at the center of the conductor, you see. So that's the potential for outside, and the potential now what we have learned is at the surface of the conductor, at R equals capital R, V is equal to KEQ divided by R. So it's KEQ divided by capital R at the surface. So since it doesn't change once I move inside, it's an equipotential. So the potential everywhere inside the body of the conductor is going to be KEQ divided by capital R. Okay, so that is KEQ over R. And this is for R less than R. And actually, you can see that both these results give the same value when R is equal to R. So V is actually continuous function. It's got the same value at R equals R, while the electric field is discontinuous at the surface. Okay, so this is something that was very familiar to us with a spherical shell, even if it was a non-conducting one. But here, this is a spherical conductor, and these are the forms of electric field and the potential that we have here. Right? So I grabbed the graph from the spherical shell over here. So what we have seen is electric field is 0 inside the body of the conductor. Outside it goes like 1 over R squared, KEQ over R squared. Potential is, it's a constant. Any point, whether you're at the center of the conductor or you're somewhere else, there is your potential. That's a constant, and it falls as 1 over R once you go outside. Okay, so there's a bunch of questions that we ask, rather popular questions here. We may give you 2 points, right? So we may give you 2 points, maybe a point A here, a point B here, right? So that is point A at the center of the conductor, conducting sphere, and maybe point B is somewhere else at a certain distance, but it's still inside for R less than R. What's the potential difference between them? You just have to remember this graph. As long as you're inside, it's at the same potential. So say, for example, my radius R was, say, 10 centimeters. I'm just taking some simple values here. So 0.1 meters. Suppose I put a total charge Q of 30 nanocoulombs, right? 30 nanocoulombs. Then my potential at the surface is KEQ divided by capital R. So that's 8.99 times 10 to the 9, and then Q is 30 nanocoulombs, right? Divided by R, which is 0.1 meters. So this ends up being, if I take it about 9, that's 270, right? And then divided by 0.1, 2700 volts, right? Or 2.7 kilovolts, right? That's the volts at the surface. That means the whole conductor is raised to 2700 volts, right? So if this is 2700 volts here, right, It's the same at point A and point B, so the potential difference would be 0 in this case.